Hey Algebra 2 students, here is a quick warm-up to review matrix multiplication before we begin our new topic. So pause this video and try the warm-up on your own. Unpause when you want to double check your answers for the multiplication. So here are the two multiplication warm-up problems. The first one, remember you do row from the first matrix times column by the second matrix, and you can see the color coding there. You do get a two-entry matrix. It has one row and two columns, and both of them happen to be 18. Second one's not possible. Notice when you do the row from the first one by the column from the second one, you don't have matching numbers of entries. One shortcut that some students prefer to use during the years is they'll write the size of the matrices. So for this first one, remember it's row by column. So here's just a little shortcut now that you've done it kind of, for a couple days. So this first one has one row and then three columns. The second one has three rows and two columns. And then for our second matrix multiplication, we've got three rows by two columns, one row by three columns, right? They're flip-flopped. So what you'll find is the way to tell if they work is this matching here. The threes are corresponding to how many entries there are, right? Because if, for instance, for this one, there's one row and three columns, the fact that there are three columns tells you how many entries there are in that row. So it's kind of an interesting shortcut there. Whereas this one has the two and the one, you can kind of see the two columns makes the two entries in that first row. And then the one row makes only one entry when you multiply by the vertical column. So that kind of corresponds to how many entries there are, and you can kind of see a mismatch there. The other kind of cool thing about this shortcut is when they do match and you can do the multiplication, this 1 by 2 corresponds to the size. I'll use pink to color code it. This one is a one row by two column. So the outer numbers actually will match up with how big it is. So now you can kind of use that as a shortcut now that you've practiced for a couple days. Okay, so our new topic is inverses. So this is going to be the big idea for our slides today. And we're going to be using multiplication to see what an inverse is. So go ahead and pause. What I would like you to do is do K times P multiplication, right? Feel free to, if you want to use what we just did, the trick, right? We're doing a 2 by 2 times a 2 by 2, right? You should be seeing that those match, so we are looking good for our multiplication. So go ahead and do that and unpause when you're ready to check. So when you do the multiplication, it is going to be a 2 by 2 if you want to use that trick, right? The outer two numbers can indicate the size. So it is the same thing as K, which is kind of surprising. You get back K. What you might be realizing is that matrix P is all ones and zeros. This looks like our reduced row echelon form that we're used to when we use matrices to solve systems. This is actually referred to, because this isn't really representing a system right now, right? This is called an identity matrix. And it's kind of like the idea of if you do 5 times 1, you get back the 5, right? That's kind of like how we did K times P, and we got back our K. The P was kind of acting as multiplied by 1, except for this is a little bit more complicated since it's a matrix. Notice how the zeros and ones helped us, right? The ones gave us the same entry, the zeros took out the other stuff. Okay, and these identity matrices are going to have a role to play in an inverse. So keep that in mind. This is going to be a useful idea as we explore what an inverse is. So I would like you to calculate this now. So go ahead and calculate and double check. So if you look to the right of the screen, we have the Desmos matrix calculator, and I've put in A and B and multiplied them. Notice that the product gives us the identity matrix filled with the ones and zeros. So I'll write that out here. So this is kind of similar to the idea that if I do like 5 times 1/5, I get 1, which we'll think of 1 as like the identity, similar to 5 times 1 giving us back our 5. So this idea here of a 5 and a 1/5 those are inverses of each other. You can think about it like times 5 divided by 5, right? Multiplication and division being inverses of each other. So the idea here is that if I call this matrix A, this is the inverse of A. So we are assuming now that if you multiply a matrix by its inverse, it yields the identity matrix. Okay, so to kind of formally talk through a matrix for an n by m matrix A, there is a matrix and we refer to it as inverse with this to the power of -1. And we've seen that before with like inverse function notation, for which the inverse times the original gives us the identity matrix, and it also goes the other way. So it has to work back and forth. It has to work for both types of multiplication, because remember, matrix multiplication is not necessarily the same if you flip-flop them. We saw in the warm-up that flip-flopping the matrices, one worked and one did not. And there's also the little clarifier that not every matrix has an inverse as well. And then due to the structure what the identity matrix looks like, we've seen identity like this. For a bigger matrix, it can look like this for a 3 by 3. So you'll notice based on the structure of identity matrices, we're only really going to be considering squares. We can call that one a 2 by 2 and this one a 3 by 3. So we're only really going to be considering those size matrices. Non-square matrices generally don't have inverses. So to practice with some calculator skills, we're going to look at finding the inverse of matrix A on the calculator, as well as using Desmos.com. So we're going to go into the matrix menu, second matrix. On the left, we're going to edit, arrow over twice. We need 2 rows and 2 columns. And then we're going to do 5, 6, 4, and 5. I'm going to do second mode to quit. Go back to matrix, so second matrix. And then remember the math menu is where we've gone before for the reduced row. If you scroll through, you can see lots of different options here. Notice you don't see anything that says inverse. It's actually really intuitive how we find the inverse. We're going to go back to names. We're going to click A, that's where we put our matrix. And then we're just going to do the button. Notice it's connected to the matrix. That's going to be inverse. And it's telling us our inverse matrix. So the inverse button is the same as the matrix. We did not see that anywhere else in the menu. So it's a little bit faster to find an inverse. So it's 5, -6, -4, 5. Okay, so here is 1, right? And then the question is there a pattern you're noticing? So looking back at number 3, as well as number 2, these were inverse pairs as well. So kind of compare those and see if there's a general pattern that you are noticing. So most students will notice, I'm going to call this A, B, C, and D. Most students will notice, for instance, that the 4 and 6 become opposites. So most people kind of say, okay, for the inverse, it's looking like we have a -B and a -C, for instance, if I'm using those letters. In this case, these are both 5, so you can't really tell much. If you look back at the previous one, you'll notice the 5 and 3 flip-flop places. So most students will kind of say, okay, you kind of switch these and opposite sign for the other 2 entries. So that's kind of the general idea that students will have after we've done a couple. The question is, does that always work? So go ahead and use Desmos or your calculator to test if that works for matrix B. So for variety, I'll show you guys for matrix B. I've got it written out here. It's calling it matrix A, but it's the same as matrix B that we're calling. So I've got this matrix. On the next line, I'm going to refer back to my matrix, and then I'm going to put the inverse button. And this is the inverse. If you have decimals, it might look like this at first. All you have to do is click this little fraction button to see them clean. So we see that it's not our intuitive nature. It's not flip-flopping these and switching the signs, right? We've got these gross little fractions here. So the question is, why is that? So here's the formal process to find an inverse matrix by hand, and this will show you the reasoning why it didn't work out before. So we do have the flip-flopping, right? You can see that flip-flopping between A and D here, and we have the opposite signs of B and C's entries. However, there's also a coefficient here. This coefficient is 1 over A times D, so kind of A times D minus B times C. It almost looks kind of like cross multiplication from Algebra 1. So there is this added piece, and sometimes we have fractions due to that, like we saw with this previous one. Sometimes it causes fractions, and sometimes it does not. So we're going to look at a couple of examples just to kind of see what that looks like. So for this matrix, I'm going to walk you through it, and then you'll do some practice problems. So if I want to find the inverse, I've got to flip-flop the 4 and the 2, so it's going to be 2 and 4 here. And then the 7 and the 1 become negative, but I also have that coefficient. That's the part that was kind of hidden. So for my coefficient, I'm going to do cross multiplication-esque, and it's going to be 2 times 4 minus, notice that minus sign here, 1 times 7. That's going to become 1 over 1, which is just a 1, right? So really it's going to be 1 times this matrix, which means it's just kind of the trick that we thought you used to find inverses. So in this case, it follows the easy rule. And that's because when you subtracted these, you got a 1. In other cases, if I go back to this previous problem, right, if I do 1 over A times D minus B times C, if I do that same process here, what we're going to see is we're not going to get a nicer number. We're going to get 1 over 9 times our flipping and switching of signs. So what you'll see is this 1/9 is why, if I look at the simplified fractions, why we have 1/9 here, or 5/9 and negative 1/9. The other two you can assume simplified to get to thirds. So that's why sometimes you get fractions. It's when the denominator does not become a 1. So anytime the denominator is 1, it becomes really simple, and it's kind of following that trick that you guys saw, and probably could kind of say in your own words. So number 6 is going to be a practice problem on your own. So go ahead and find the inverse of matrix S, following the steps that we've just done together. Okay, so here's the inverse of matrix S. Notice when you do the A times D minus B times C, it does yield a 1/2, so this one will become a fractional inverse. We also have to remember to switch the A and D entries, the 4 and the 5, and to make the 9 and 2 negative. For your final answer, you can leave them as simplified fractions, or you can leave them as decimals. I've written them in both forms. The last question I'd like you guys to consider is to think through when a function does not have an inverse. Thinking through the structures that we've seen in these two problems, as well as in the general rule. When does a function not have an inverse? So try and write that in your own words before unpausing to double check. So a function does not have an inverse when the A times D minus B times C piece yields a 0. And that's because you would have 1 over 0 as your coefficient of your matrix, which is undefined. So your scalar multiplication coefficient would be undefined, and then if you can't multiply, you can't continue on. So that is something that you can look at really quickly to say if a function has an inverse or does not. You can do that multiplication and subtract and see what it yields.